Good afternoon, everyone. Thank you for joining I²CNER seminar series. The I²CNER seminar series was launched in 2010 upon the inception of I²CNER. Since then, seminar series has featured the best researchers in the world on the carbon neutral energy issues. My name is Shoji Mori from Kyushu University. I'm the professor at the I²CNER and the Department of Mechanical Engineering. I will be your host today. Today, we are very pleased to welcome Professor Christos Markides, Professor of Chemical Engineering at Imperial College London and Editor-in-Chief of Applied Thermal Engineering and AI Thermal Fluids. We invite Professor Markides because of his pioneering work on advanced experimental methods and accurate measurement in thermal and multiphase energy systems, which closely align with I²CNER's mission on carbon neutral energy research. He is internationally recognized for his outstanding contributions to thermal and multiphase flow research and leadership in clean and carbon neutral energy technologies, and has delivered numerous invited and plenary lectures worldwide. We are confident that his insight will provide valuable perspective and spark active discussion today. Now, I'd like to invite our Vice Director, Professor Fujikawa.
Good afternoon, everyone. And also, my name is Fujikawa. I'm an Associate Director of the I²CNER. So, first of all, welcome to the I²CNER. So, most of the parts will be explained by the Professor Mori. That's why I don't have so much, words to express our, sincere thanks, appreciation. So actually, as you know, the I²CNER is dedicated to the advancing the fundamental science and also technology for carbon neutral energy system. So of course, in that case, we should have interdisciplinary research. Actually, I'm chemist and polymer scientist, but we have to promote such kind of interdisciplinary research. So actually, we are very delighted to host Professor Christos Markides. Actually, he is a Kipros, and also our ex-president director is Professor Petros. He is a Greek people. So it's very good. So as he explained, Professor Markides is a world-leading expert, especially in the experimental multi-phase flow and heat mass transfer. Actually, I'm working on the CO separation, but currently I'm facing the very serious issue about the airflow and energy flow through the membrane system. I'm very interested. Okay, today he will talk about this process, but we are very looking forward to his talk today. And also, I hope it will stimulate active discussion, especially from the young researchers and students. All right. Okay, thank you very much for joining us, and I'm happy to have accept your, presentation. Thank you very much.
Thank you, Professor Shigekawa. And before we begin, I'd like to take a moment to remind you that your question will be addressed after the presentation. And please use raise hand button and type your question comments in the Q&A box. When you are called on, please unmute yourself. This webinar will be recorded and made available on I²CNER website. Now, everyone, please welcome Professor Markides.
Okay. Well, thank you. That's a really a very kind introduction. I don't know if really I'm pioneering, but I think I find if you stay in a field for long enough, at some point people recognize you for some things. So I'm going to tell you about some work that started about 20 years ago. At that time, I was very interested. So I come from the field of combustion. I don't know if you still have combustion. But yeah, was a lot of interest in combustion, quite complicated flows, reactions, quite complicated reactions. And I was starting to understand how to develop laser-based methods and apply them to these kinds of flows. And then after I went into the chemical engineering department, so this is my PhD, I faced a completely different set of fluid problems that basically have interfaces, which in combustion, I was doing single phase combustion, hydrogen, hydrocarbons, gases. So it really excited me because there were very, very big challenges to solve if you want to do optical measurements when you have interfaces. So I'm going to tell you basically some of the work that started back then about how slowly we try to adjust techniques that many people know, but we try to adjust them to apply them to different types of multi-phase flows when you have an interface. And then following a presentation of almost like a history of how we developed some techniques and some tricks and solutions, I'll tell you about two recent problems that I try to address, I guess, with my team. Really, I should say mostly it's the team, and I'm just there to give them some advice from time to time. So let's just start. There was a very quick mention of applied thermal engineering. Okay, so many people know that I've been editor-in-chief of this journal almost 10 years. I think this is my 9th year. I try to make all of our papers available, even open access, as in not behind the firewall. So the research gate link there will redirect you. You can go and download the papers. A lot of the things that I'm talking about today are available. What many people might not know is this new journal. Professor Mori mentioned it. AI thermal fluids is very new. I don't have time to go into this, but I just wanted to show you that it exists. And if there are people here interested in this, then let's talk about it afterwards, okay? But let's go to the research now, okay? So I mentioned before that one of the problem definitions or problem statements that I basically faced throughout my career is how do we apply optical methods to flows where you have interfaces. Non-moving interfaces are not a problem, okay? So if you have a mismatch in refractive index, maybe I should take a step back for those of us who are maybe not experts, but whenever you have an interface between two media and there's there's a difference in refractive index, you will have optical distortions, right? And this is a problem if you're trying to do an optical measurement. If this distortion is constant, it's fine. You can correct for it. The problem arises when it's moving, right? And you can see here some example flows where you see, this is a so-called liquid-liquid flow. We have an interface between two different liquids. And you can see, and there are also, of course, gas liquid flows and so on, but you can see two different very types of styles of approach to these types of problems. The first one is fluid replacement, right? If the conditions allow us and we can achieve dynamic similarity, which means trying to match the flow with reality, then we can replace one of the two liquid flows, for example, with another liquid that has the properties that we want, but the same refractive index as the other liquid phase, right? So we can avoid it this way. And you can see here what I'm trying to show, that if you have a flow where you match the refractive indices between the two fluids, then the fact that you have an interface is not really all that important, or let's say the errors are small because you never really match it 100%, but the errors are much smaller, you minimize them, and both, the illuminated field, plane, or whatever it is, and the imaging line of sight are not really distorted very much. So that's okay. However, in some cases, you can't do this. A classic example of this is if you're using a gas, right? Matching the refractive index of a gas, which is almost close to 1, and a liquid, 0.3 upwards. Typically, water is 1.33. It's very difficult to match. So really, we're in the business of trying to solve this problem. How can we solve this problem when you have a gas-liquid flow or two liquid flows where the refractive index is not matched? Here, I'm showing you just one solution. And I'll show it a little bit later, in which we can image the different liquid domains with different imaging systems and then reconstruct the full domain later. I'll tell you more about this later, but that's the problem. I just kind of thrown in a potential solution just to kind of excite you for now. All right, so over the years, what did we do? We started from flows which are more simple. Remember what I said at the beginning. Whenever you have a curved interface, right, or an angle between the light and the interface, and this is moving, that's a problem for you, right? So the smaller the curvature, the smaller the disturbance, the easier it is. So we started from something called falling films. Falling films are very simple, and by the way, these are planar falling films. So not inside a pipe, but a flat plate. And there's a liquid that basically flows over this flat plate. And by the way, so this is a little bit deceptive, right? These are falling under gravity. So in reality, they're like this, but the camera is at the same angle, so they look flat. They're driven by gravity. There's no shear, quite simple. Low-dimensional flows with simple, smooth interfaces, relatively. And you can do measurements like this with something called planar laser-induced fluorescence. Now, I know there are some people in the audience that know this very well, but for those of you who don't know what this is, we put a chemical inside the liquid that we're trying to observe. You don't have to. Sometimes you can directly excite the liquid, right? But most of the time, we can add something in there that absorbs the energy from the light, from the laser, sorry, which is exciting it. So there's some laser, right? In this case, it's a plane of light, so it's a sheet, okay? It excites it and then re-emits light at a slightly different, normally redshifted wavelength. And this is a broadband emission, which means many colors coming out, yeah? And then we collect that light, and wherever there is light, it means we have the presence of this chemical that did this business, which is called fluorescence, right? Fluoresced. So basically, this is a 0-1 game. If you see color, there's a liquid with a dye in it. If you don't see color, there's a gas, which is the air above it, or a solid, which is a substrate below it. And from there, we can recover film thickness, and you can put particles inside, and you can do velocimetry methods. These are very classical approaches. We're not doing anything fancy. And you can do time-resolved measurements. So you can space and time-resolve film thickness and velocity. These are isothermal falling films, flat plate. Very simple. Great. And from that, you can get very useful information. So you can see here, for example, this is one flow, right? This is not different types of flows. This is one flow. And this is a normalized flow rate, which is basically the integral of the velocity profile that we just measured, some position as a function of time. And at the same time, it's a normalized film height. So what this shows you, right, is that the film thickens and thins, and as it thickens and films, it transports more or less mass. Yes. So you can get information like this, which is kind of beyond the classical measurement, where normally you'd only have one point here, right? You'd sort of an average flow rate, an average film thickness. Here we have quantitative variation of how these two things are correlated simultaneously. Okay. We won't talk physics today, just photography. Okay. Right. Now that's easy. That's easy because it's a pure so-called isothermal flow. There's nothing else to measure. If you can measure the velocity field everywhere, okay, and if you know what the film thickness is, that's it. Okay, that's all we need. And we've done a lot of work working with modelers. Yeah, you can do DNS. These are complicated flows, right? But in any case, we want actually, I'm a thermal engineer, so actually these films are used where you have heat transfer, okay? And when you have heat transfer, you have temperature to measure. And from the temperature, you now start deriving quantities in addition to the temperature. But we have to measure the temperature, okay? So I'm showing you here a couple of approaches. A lot of people use infrared thermography. We can use infrared thermography too, right? And here what you're actually seeing is the temperature at the interface between the liquid and the solid, which is not constant. This is not, yes, an isothermal boundary condition. The film and the solid wall below it are interacting thermally. This is called a conjugate problem or a coupled problem, right? And here what you're seeing is the same method that I showed you before, right? So before I told you about this, before I showed you about this planar laser-induced fluorescence method, right? Where you add some chemical into the flow. Here, we make sure that this chemical that we add to the flow, the emission is temperature dependent. Doesn't have to be, but here it is. And so this signal here that you see, now we care about the brightness because the brightness is correlated with the local temperature. And from there, we can recover an interface temperature, okay? So if we do this, right, we can measure the interface temperature with planar laser-induced fluorescence from the intensity. We can measure the wall temperature by using infrared thermography from the back. Or if we're rich and we have two infrared cameras, we can stick one camera below and one camera above, and we can get temperature fields, right? Because infrared will be absorbed in a thin region at the close interface, right, between the gas and the liquid. So we can do temperature measurements like this. And we can get very nice information, like the one I'm showing you here, right? So you can see a film. So this is a film thickness. This is the temperature difference across the film. Be careful, this is not the classical Nusselt definition type, yeah, bulk temperature difference. This is just a pure temperature difference between the interface and the wall, locally and instantaneously. And this is the heat transfer coefficient defined on this quantity, okay? And so what you can see here is that over a certain spatial domain, we can measure these things and we can time resolve them. So what are we seeing here? We're seeing a film wave, which is moving from right to left over time. And as this moves from right to left, the temperature across the film responds, right? When it's thick, the temperature across the film is quite large. And when it thins, the temperature across the film is quite small, right? This is negative, so it's a little bit deceptive, right? And of course, the heat transfer coefficient responds in an opposite way. So when the film is thick, okay, the heat transfer coefficient is relatively small. And when it thins out, it becomes much, much larger, okay? Now, this is a classic case of basically conduction-dominated flow. There's not a lot of convection in here. So, okay, I don't want to go into the physics. But you can see how we can understand links between heat transfer locally, right, and the wave dynamics and so on. And we can plot, this is called a joint PDF, where, again, so each one of these maps, if you want, right, or contour plots, if you want, is from one flow with one Reynolds number, okay? And what you see here is the film is thinning and thickening and thinning and thickening. And as the film thickens and thins, the heat transfer coefficient locally, right, is responding to this wave. Now, this is very useful for design, okay, because you can control, if you can control the waves and their thickness, you can control the heat transfer, okay? Good. So that's the kind of information we're after. But there are problems, okay? There are problems in these flows. And I'm very glad that Professor Moore invited me to come here to visit you, because we're having exactly this discussion today, that in some cases you have some problems that I will explain in a minute. But before I present the solution, so most people's eyes goes to here, let me explain what the problem is. When you're trying to image, yes, some flows from the side, when you start to have large curvatures, you start to have some errors, okay? And these errors arise from the fact that you don't need to know the details, but you just need to know the kind of physical origin of these errors. If you've been onto a swimming pool and you've gone underwater and looked up, sometimes you'll see a reflection, okay? This is exactly what happens in these flows. So the camera can see something, but it can also see the reflection of that thing at the same time. And it's very difficult for us to know what's real and what's a reflection, okay? And this gets worse the more curvature we have, right? So in my team many, many years ago, there was an excellent postdoc. His name is here. Korean is now, he works for LaVision, not the Japanese LaVision, the one back in the UK. And he applied the technique called structure laser planar-induced fluorescence to try to correct for these reflections, okay? It basically involves us having gradients of light. So you can see this kind of gradient at an angle. The angle is very important, okay? And what happens, what he's trying to do here is, as you look at the fluorescence from this film to try to measure that film thickness, remember that we spoke about the film thickness like 3 or 4 slides ago, right? So here what's happening is this fluorescence is being reflected. So we have a real film and we have a reflected film. And these two things add up, and you can see that the errors can be 100% or more sometimes, right? So if you didn't have this structure that he imposed, you'd think that the film is up here, but it's not. The real film is actually down there. And how does he correct for it? Well, if you've ever looked yourself in the mirror and raised your left hand, you think that your right hand is waving at you, right? He does exactly that. Also, the reflected part of the film has these lines coming up at a different angle than the direct image of the same angle, right? So he's trying to use this principle to correct for it. But the important thing here is that, well, okay, this is what we're trying to do. Find solutions, right, to problems in which we have interfaces which are causing us, optical errors like this. So this is a classic example of a solution. This is another bit of interesting work. So sometimes you have phenomena that have development lengths. Now, this word development length means different things to different people. But in terms of, when I say development length, I mean, let's say macro scale, large wave phenomena stabilizing in terms of the statistics of the frequency, wavelength, and so on. Now, these pipes are quite big, so they're 30 of the order of 30 millimeters, right? A little bit more. And the development length of these kinds of pipe could be meters, could be 6 or 7 meters. Now, one thing you could do if you want to understand these types of flows over the development length, you could do measurements at different lengths from the inlet, or you can do what we're doing here, right? Which is have a moving frame of reference measurement, okay, where you're tracking a feature over the whatever 6 meters length that you have, okay? So what we're applying here is a slightly different technique, which is called brightness-based lift, where you kind of rely on the fact that the laser that you're sending into the flow is being absorbed. The thicker the flow, the more it gets absorbed. The thinner the flow, the less it gets absorbed. So there's some correlation, right, between the thickness and how much light is absorbed and emitted. Okay? So we can do this through calibration. But this is a sort of a measurement that shows that sometimes we need information over very long lengths, right? And we can get this in one run. Okay, so I'm going to return to that problem that I mentioned before. And what I'm showing you here is actually different flows, but they're also, yeah? So on the left-hand side, it's a liquid-liquid flow where I mentioned you could just match the refractive indices. Right, so here we're not doing anything. We just have a single laser. It's cutting through the two liquids. And we have a single camera looking from the side. And we can do measurements in both phases simultaneously without big problems. Okay, I'm going to actually jump over here. Okay, and what we're doing there is in exactly similar flow, right? We did not convince the company that wanted us to do this data that we could change the fluids because they're very empirical. And they don't like the idea that an academic is coming in and changing their fluids, right? They don't believe in dynamic similarity. To some extent, they're right because there are 13 non-dimensional numbers in this problem. So what we did here, we said, okay, we cannot match the refractive index. So we have an oil phase, an oil and a water phase, and there's a mismatch in refractive index. And what we did is exactly what you can see. I mentioned it before. So we can try to illuminate an image, right, the two liquid domains through different imaging systems. As soon as the laser, which is imaging, let's say this bottom part here, hits this interface, right? So you're looking at the laser is coming this way and the camera is looking at this region. As soon as it passes through the interface, all that information I'm going to delete. By the way, I can see where the interface is because I have an intensity which increases that interface due to reflection. Okay? So I know exactly where the interface is. Everything above that, I delete it. Okay, from one camera. Luckily, I have a second camera, which is only looking at the top part. And I have an interface in that camera because I can see that locally there's a reflection, so I can see where it is. And everything below that, I delete it. Okay? I do not trust that data. And then I take those two parts and I stitch them together. Okay, so this is another solution, which we mentioned before. And this is exactly how it's implemented. Actually, this is a single laser. You need two beams, right? One from the top, one from the bottom. But it's a single laser because a copper vapor laser basically has two colors that come out. We split those two colors. We send one through each domain, and we basically have two cameras, like I told you before. And by the way, I should say it's not just about identifying where the interface is. It's also that you have particles in each phase, and you need to measure the velocity fields in each phase simultaneously. And then we went, so we went from planar falling films, and I told you about curvature. Then we spoke about, this kind of more complex flows. And so now we're going to go to a case where we have boiling, which is, let's say, the highest complexity type flow that I've talked about so far. And this is work that we did with Professor Bucci. Actually, we did this in his laboratory. There was a postdoc from my team that went to the US over a couple of years. The first time he went, he spent 2 months there. At the end of the year, we took all that data and we pressed delete because it was very difficult and the data wasn't very good. So you had to go back. But anyway, so in these types of flows, what tends to happen is we want to measure temperature, important, right? Along with velocity and so on. Now, the classical measurements in this field are wall measurements. So most people that work in this area, most, not all, but most people, they have some kind of substrate, right? It's called pool boiling, for those of you that might not know, right? So there's no mean flow. And what happens is it's like a kettle, right? So you have a surface which is heated, you apply some electrical heat flux, there are some bubbles that form and those bubbles rise, okay? And they try to measure the temperature and the heat flux over the surface and how it responds to these bubbles, which are growing, yes? And then detaching, and then the fresh liquid comes in. So most people do these measurements on the wall through infrared thermography methods, which are to some extent well known. Okay? What we're trying to do here is combine these measurements on the wall with information of what happens in the fluid as these bubbles grow, right, and detach and so on. So we're trying to simultaneously get all of that together. And I'll show you some results, but I think I'm going to say only one thing because it sets something up later, which is that when you start having a lot of interfaces inside a flow, you have a problem, okay? Remember what I told you initially, when we try to do these temperature measurements, okay, we add this chemical, right? We send light through, the light gets absorbed in the liquid, and then re-emits. And we collect this emission, and if it's temperature dependent, then this emission is also a function of temperature. Remember that? Okay. The problem if you have a lot of interfaces is that you can have significant reflections, right? Which means that if the intensity is very high, you don't know if it's something to do with the temperature locally, or whether it's some reflection that you got off a bubble or something like this. You don't know that, right? So what do people do? Well, think about it. We have two unknowns, the reflection, which is another way of saying we don't know how the laser intensity is distributed in space. Right? It's a function of X and Y, right? And also the temperature is a function of X and Y. And we don't know if the signal is coming from one or the other. That's a classic problem. We have two unknowns. How do we solve it? Two equations. So we have two dyes, right? This is called two-color lift, right? And we apply two dyes. In this case, one is temperature independent, so we can get the variations in intensity. Right? Temperature independent means your signal is only a function of the intensity of the laser. And one is temperature dependent, and then we use those two to get a temperature map. Okay, so I'm going to go very quickly now, show you some results. Yeah, there we go. Okay, so this is all synchronized. This is a classic infrared technique. Professor Bucci has this perfected, right? And this is an image from the side. Be careful, this is not high-speed photography, right? We didn't just sit a camera there and start taking images. This is a real temperature field, but it hasn't been corrected for temperature yet. So this is a fluorescence that's being collected by the camera. And from there, we can get temperatures through calibration, and you can get simultaneous information, right, about what's going on the wall, what's going on inside the liquid. Very nice physics you can uncover from this, right? And the final thing I'm going to show you is, well, why not make it even more complicated, right? What's the fun if we just keep it at that level? Let's have a flow where you have a solid forming. So here we have a freezing problem. They have a lot of such problems, of course. There could be phase change materials, they have solidification. There are problems where you have freezing in pipes and nuclear reactors and so on, so, molten salts. But here you have an even more complex problem. And here I'm showing you basically the solidification of water. So it's just freezing, water freezing of a sessile drop. That's what a fancy word for a drop that's just sitting on a substrate. And I'll show you more later, right? Something which is kind of close to this, but even more complicated, right? So we want to try to do measurements in these types of flows. It's very difficult to do measurements in flows when you have a solid forming, right? And you're trying to optically look at inside the flow. Okay, let's keep going. But it is possible, and I'm showing you here shapes of droplets, relatively easy, and velocity fields inside the droplets, not very easy. Okay. Okay. So let's go now to more recent work. That was the easy part. This is a microchannel facility. So what we decided to do is we decided to go from these big, generally macro flows, right? These kettles with the boiling water inside, to something quite small. So here we're millimetric. And I will show you. So it's not water as well, right? That's another channel, but I don't want to go into it. This is a special type of fluid which is used in electronics cooling. So it has a very special boiling point near ambient pressures, right? But that's beside the point. Let's leave that out. So we built this facility. This was funded by the UK EPSRC, which is kind of a JSPS style funding. Vertical flow through a mini channel, single mini channel, no complexity. And we want to do same measurements I was showing you before, but in here. What's the difference? The difference is when you make your flow small, it means you have a lot of walls, right? When you have a lot of walls, you have a lot of reflections. Optically, it's more difficult to do measurements in a small domain, in a large domain. Same discussion we were having this morning, right? Okay, I won't say very much. This particular size of channel, 5 by 5, heated on one side, yeah, classical macro channel. So it's heated on one side. A lot of people do this, by the way. Different types of glass which are transparent to visible. With an ITO coating, which is basically where the heat flux is imposed on the side of the liquid, yeah? So this is where we're heating the flow, if you want. And then we're doing measurements inside some section. Like, let's remember, the flow is going up. We have a measurement section, so we have the development length, right? We want the measurement towards the end. And what are we doing here? Well, we're doing our infrared measurement plus same stuff that we were talking about before, right? So we want to measure velocity fields, we want to measure temperature fields. But here it's more difficult, right? So we kind of left the velocity fields out for a minute, trying to get the temperature measurement right. So what are we doing here? Remember, I told you before that we can have, there are a lot of reflections, and when we have a lot of reflections, we have two dyes. Remember that? Okay. We want to go away from this use of two dyes. Why do we want to do this? Two reasons. Number one, I don't think I have ever gone to a conference and spoke about using dyes in a flow which is boiling without getting the question, how does this affect your flow? First question you get, right? Imagine you put two dyes in there plus some particles. You're going to get a lot of questions. Now, we've tried to address this, okay? But you always get those questions, all right? So we want to try to not use as many additives, let's say, in the flow, right? As much as possible. That's the first one. The second one, and I don't want to go into a lot of detail here, is that there's a very interesting phenomenon whereby even if you mix your dye in uniformly into the liquid, if you impose a temperature gradient, which we have, depending on the size of that temperature gradient and the properties of, the fluid that you're using, you can result in an unmixing of the flow. So you end up having a concentration gradient, okay? This is called thermodiffusion, and there's something called the Sorare coefficient that kind of tries to quantify how big this effect is going to be, right? Now, in these flows, it can be significant, right? Now, you wouldn't know it if you just did measurements, right? You wouldn't know that you're getting a concentration gradient of your dye inside the liquid because you just get a measurement. You don't know how big the concentration gradient is. So what are we trying to do here? Well, we want to definitely try to remove one of the two dyes. That's really where we're heading here. We want to remove one of the two dyes. And we want to end up with just one dye in the particles. And so what we do here is we have one dye, but instead of collecting all the light from that dye, we recognize that the emission from that dye is a distribution. So it's in different colors if you want, right? And the emission at each color changes with temperature. I'll show you in a minute what I mean. Get rid of that. Okay, that's the dye that we're using. Okay, so here's what we're doing. So on the left here, right, is the absorption spectrum. So that's kind of the colors that your dye can get excited at. This is very important. If you have a certain laser, you want your laser to be somewhere in here, okay? If you're very rich, you have a lot of lasers, or you have a pump laser and a dye laser, so you can tune this to whatever you want, right? So you're less susceptible to, or you have more options, let's say, in terms of the dyes. But if you're not very rich and you just have a YAG laser that most people have, then you have something around the green, and then you have to find the right chemical that absorbs well in that range, okay? So fine. So this particular dye that we chose here is good. It doesn't have to be right at the peak, somewhere close, right? You want to absorb a significant part of the laser energy. And then this part here on the right is the emission spectrum, right? It's the light that comes out of the dye when it disexcites of the molecule. Okay, so what I'm showing here is that this shape of this emission is a function of temperature. But it's not just a scaling up or down, the shape changes. This shape change, we're going to use it to link it to a temperature to try to do temperature measurements. Right? So basically what I said is instead of using two different chemicals and one laser, we're using one laser, one chemical, but looking a little bit at the difference in the emission of different colors, which is a function of temperature. Okay? And here I'm showing you the same thing, but I'm also showing you that there's a concentration effect. Okay, but I'll come back to this in a minute. It's the concentration of the dye in the liquid, right? Ignore all of this, is very complicated. It really just says that, how we select the two bands, the two parts that we are looking at. So each camera looks at different part of the emission. Okay, how do we do this? With special filtering, right? Like glasses in front of the camera. The important thing is this thing here, right? So basically, this is the ratio between these two, the signals of the two cameras, which I said is a function of temperature, right? Now, you want this to be as steep as possible because that means your measurement is sensitive to temperature changes. That's good. But what is interesting is that it's also independent of the concentration of the dye. This is great. Yes? Not easy. But above a certain concentration, so above about 2 to 3 milligrams, per liter, you start having a collapse of this calibration. It's very good. So even if you get a little bit of thermodiffusive effects inside your films or inside whatever close to some boundary, then your temperature measurement will not be affected. Okay, so I'll show you some results quite quickly. So this is us basically taking some raw measurements. You have to do a lot of spatial calibrations. Remember, you have two cameras looking at the same thing, but with different filters in front. So they're looking at different colors, but in the same region. So you have to align them very, very carefully. Okay? So there's a lot of work that goes into spatially aligning them, even dynamically. All right, so here we are. I'm going to show you some temperature results. Let me just go all this. This is a calibration curve, which we use to go from a temperature, from an intensity, or rather a ratio of intensities in the two cameras to a temperature. And how do we get this? We simply, establish a flow where we measure the temperature with, let's say, a thermocouple. We draw this, and then we remove the thermocouple, right? Okay, and here's the result. Okay, so here you see a boundary layer, and it's a vertical flow, right, going upwards, single phase. Whenever you see any bubble, whenever you do not see any bubble, sorry, it's a single phase flow, right? So we have a thermal boundary layer that grows. We know how they should grow, right? Just from classical undergraduate level fluid mechanics. Okay, and then we have a bubble that forms, and then this bubble starts to slide. And what we're interested in is how this bubble interacts with the thermal boundary layer. This is very important in how heat will be diffused into the bulk of the liquid. Okay? And this is really what we're trying to do, and we have been trying to do it. In some cases, this is quite a complex problem, actually, because this interaction is scale dependent, right? If the two things have a size which is very different, then they don't really interact, very common in physics. But if the length scale of the boundary layer thickness and the length scale of the bubble are similar, right, of the same order, then they will start to interact. And you can imagine that these types of thermal plumes are very important in pulling heat into the fluid. Okay, good. I don't want to say too much there. I think I said enough. Different conditions, we can discuss it later if you have any questions. How am I doing with time, by the way? How long do I have? Another 20 minutes. If I go too quickly, then I start again. So I told you about the temperature measurement method, right? In the liquid. At the same time, we're measuring the temperature on the wall. Again, I won't go into too many details of that because it's a sort of a classical measurement, right? We didn't invent infrared thermography for wall temperature and heat flux, of course. Many people do that, so I won't spend too much time. I'm also not going to show you velocity measurements because we haven't done that yet. Just doing what I showed you with a 3-year PhD, okay? But in principle, there's no reason why you cannot add some particles and get simultaneous velocity in the flow as well at the same time. I just want to go quickly over these slides just to show you that, yes, we're measuring heat flux on the wall as well. I should say this is a little bit more difficult than water flows, because the signal to noise ratio, remember it's a different fluid, right? So signal to noise ratio is not as good as what you would get with water. But that's beside the point. And we're processing this data. So this is very much raw data that I just asked the postdoc to send me. But I want to talk to you about something more complicated. Okay, I want to tell you about a problem where you don't only have solids forming, but there's a reaction. So this is called hydrate formation. So hydrate formation is a process, a reactive process, okay, where two liquid phases react to give a solid. So it's not a freezing in the sense that it's phase change from water to ice, but it's a reaction where the product is a solid. Okay, and we want to try to understand this phenomenon. And of course, the classic measurement we want to do, of course, is to understand reaction, right? The rate at which these solids are being formed is very important, right? Good, so let's see what we did here. So this is, let's say, the extension of the water is freezing stuff that I showed you before. Well, set up what we thought was a simple problem, okay? Just a drop of water sitting inside this other phase that it's going to with, which is basically cyclopentane, right? So we have water cyclopentane. Why we picked this system is because fish don't just grow at whatever conditions you want, right? Normally, these things form at the bottom of the ocean at very high pressures and very low temperatures. But this particular system is restricted because you can form hydrates at atmospheric pressure, right? So this is just a big tank open to the atmosphere, nice and easy, no pressurization, no complexity. Well, no complexity from that side anyway. So we have our little drop of water sitting on some pedestal, and you can see here what it looks like. And then you have this solid that forms slowly. This is a slow process, by the way. It's nothing like what I showed you before. Before, this kind of bubbles can be quite fast sometimes. Here, this is happening over the course of minutes, right? It's quite slow. But anyway, the hydrate forms, and then it starts to grow and merge, and you form a shell, okay? Now, as soon as this shell forms locally, not covering the whole thing, but locally, where the shell is, it's very difficult to observe through it. It's a solid, remember? Okay. So what do? Well, we take the view that you don't need to do measurements everywhere all the time. You just need to do measurements in some places, some of the time, to get some information. Another way of saying what I said is we can measure these hydrates in some places, all right, where we can see through the interface. And at some times that we have access through this interface. Okay, so I have some information here, but it's not very important. I should say the goal here, just to repeat, is to measure reaction rates. Yes. Okay, and I don't just mean looking at it and sort of measuring how much distance it grew over time. I mean actual, yes, heat release rate, for example, right? Because it's an exothermic reaction. And how we're going to do this? Okay, when you have an interface between two media, right? The temperature gradient, or I should say the heat flux between the two sides, has to match, okay? So if it's the same thermal conductivity, the gradient has to be the same. If it's a different thermal conductivity, K times the derivative of the temperature at the wall on the two sides has to match, right? Otherwise, you're violating the first of thermodynamics. Energy cannot be created. But here, energy is created. Okay, we have a source at the interface. Another way of saying this is that any difference between the heat flux on either side of the interface is caused by the reaction. Makes sense? Because heat is coming out. Good. So we need to measure that. How do you measure that? You need a temperature profile. You cannot measure heat flux on this kind of thing directly. Okay? You need a temperature profile on both sides of the interface. You need to take a derivative of that temperature, right? Project it to the interface and find the difference between that times the thermal conductivity of the two liquid phases. Easy, right? Okay. So let me show you what we try to do. By the way, this is ongoing work, not yet published. So this is the experimental apparatus, right? The way that it's set up. You see this drop inside the cold liquid. It's being maintained at a cold temperature. We have cameras looking in. We have, this is a little bit deceptive, 2 laser sheets. Okay, one is coming from the bottom and one is coming from the top. Because remember, unfortunately, this is the case of mismatched refractive index. So we go all the way back to me telling you that, well, you can inspect different liquid domains with different imaging systems. This is exactly this, but much more complicated than before, right? So one laser is coming from the top with one camera, another laser is coming from the bottom with different camera. Actually, it's more than one. I'll show you in a minute. And then we reconstruct this later. So early on, we noticed that if you try to have a vertical laser that goes down, right? So vertically down, and you want to image this phase here, this oil phase, the cyclopentane, right? And you want to see what's happening here. It's very difficult to go close to the interface and go all the way around the circumference. Okay, now you can try to angle your laser, but then you lose some parts somewhere else. So what we decided to do is we actually have 2 laser sheets coming from the top. One is in a vertical direction. The beam before it's expanded is vertical. The other one is basically coming from an angle. And then we basically add the 2. So each one of those goes into a different camera, and then we add those 2 cameras up. So we're kind of stitching information from different lasers, but even in the same domain, to see more of this area around the interface, around the circumference of this drop. Okay, this is just for the top. Now, the top, okay, this is a big domain with not a lot of reflections. And think about it, right? So we're trying to look at all of this fluid here to do some velocity measurements, temperature measurements. There are not a lot of reflections, relatively. There are reflections at the interface, of course, right? But it's not like a macro channel where you have things going on everywhere. So we don't need to do something complicated here. Okay? We don't need to do 2 dyes or weird clip stuff. Okay? So we just have a standard calibration where we have 1 dye, 1 camera, right? And then we try to we do a calibration, and we try to recover the temperature from just classical laser-induced fluorescence, which is what I showed you like 5 minutes into my talk. Okay, and you can get things like this. I'll show you more later, but you can get sort of temperature fields like this, which kind of makes sense because you have a hot water drop inside a cold liquid, right? And there's a thermal plume that rises due to buoyancy. I mean, you expect this, but okay, we're getting the actual quantitative results from that. Okay, that's the easy part. The difficult part is doing measurements inside the drop, and this drop is millimetric, okay? Of the order of, right? So a few millimeters. That's more difficult. Now you have a lot of reflections. Now you can't just be you can't just say, oh, well, my reflection errors are small, I can't ignore them. No, here you go back to this 2-color Pliff method that I told you about before, where you have 2 dyes inside and all that complexity with the ratio of the signals and 2 cameras. Okay. It's more complicated, right? The point isn't that you understand everything. It took me a lot of years to understand it. But the point is to say that inside the flow is more complex because there's, it's more confinement, and optically it's more difficult to look and really quantitatively measure things inside that domain. Fine. But there are ways to do it, and we're using this kind of 2-color lift method where we have 2 dyes, 1 laser, 2 cameras looking at the same plane. The ratio between these 2 things has something to do with temperature that we get through calibration. And then we can get a temperature here. And you can see features here. Okay, you can see features here, some of which, by the way, are due to the fact that we're getting reflection at the interface, and there might be something at the interface. Okay, so this is difficult to do. All right, on top of all of that, why don't we measure velocity fields as well? And let's throw that in there. So you want to measure velocity above, nothing complicated. And you want to measure velocity inside as well. But let me show you some results. So this is, be careful, the color here is no temperature, right? It's the magnitude of the speed, right? The magnitude of the velocity vector. And it's what you expected. So you have this plume that rises initially, and as time passes, there's a temperature equilibration. So this kind of plume dies down. Another way of saying it is that the temperature driving force for this flow goes away slowly, right? And this is the flow inside, and unfortunately, I have some very bad news for the modelers. It's not a symmetric flow. Reality is not symmetric, right? These are stochastic phenomena. Your hydrates do not form some kind of axisymmetric way around the hydrate, and there is no such thing as a perfect sphere in reality, so it sort of starts from somewhere. You can end up with asymmetries inside your drop. And by the way, the complexity and asymmetry increases as the size of the droplet increases. So look at this. This is 5 millimeter drop, and everything is a function of time. It's a transient phenomenon. This is a much bigger drop, right? You can start seeing multiple recirculation zones here. Sometimes you see 2 recirculation zones, but similar kind of physics, right? So we have this flow where there's a temperature gradient driving a plume. The inside flow is responding to that plume because through interfacial tension, there's a linking between the 2 domains. So we started by thinking this is simple. There's a lot of complexity in this flow, even though it's laminar, okay? And from there, we started, first of all, asking ourselves the question, can we even observe or detect the presence of the hydrates, right? Now, in some cases, the hydrates form, and in sometimes they don't form. It's a bit like a boiling or any sort of phase change process, right? So the thermodynamics are there, right? But unless you have the, in this case, crystallization point, yes, it won't form. And in many cases in these flows, it doesn't form. So you have cases where hydrates form, solids, and in other cases, they don't form. So we actually have a comparison between the 2 cases. You can see them, right? You can see by eye that they're forming or not. And we're trying to detect whether, for example, we can see changes in the velocity or the temperature fields when these hydrates form. That's the first thing to do before you do any weird measurement of reaction rate at the interface or heat release. And we can, okay? I should tell you, by the way, that these are averages of multiple, So these are called ensemble averages. Each one of these that I'm going to show you is an average of a number of realizations of the same experiment, okay? And we can detect changes, right, to the velocity close to the interface. So this kind of starts to suggest that we can see things. And I'm pointing you here. This is the interface here, and you can see changes right between the blue and the red. There's differences between the blue and the red. And a difference between the blue and red means there's a difference between when the hydrate forms from when it doesn't form. Very important. Okay, so this is a velocity field responding to the fact that the reaction is happening. So you have a solid, which is affecting tension, interfacial tension, but also, right? So it's not only affecting interfacial tension, but it might be, there might be some heat release, which might locally be causing some buoyant effects. Who knows? We don't know, right? We're still looking into it. But we can detect these changes. And here what I'm showing you is the temperature. So before it was velocity, now I'm showing you temperature inside the drop and outside the drop, okay? These are not polished results, right? These are almost raw. You can see there's no smoothing. There's no weirdness going on here. You can see the signal here, right? So it's as I said before, when this starts from 0, there's a big temperature difference, and then, there you go. And then it slowly dies away. And then inside you have your temperature field. And in some places, we have these streaks forming. It could be from different reasons. We're not 100% sure yet. But the view, again, is we don't have to measure everywhere. We can pick locations, right, where we don't have those types of complexities or some kind of error. Could be for many things. So we pick, went too quickly, but we pick a point below the interface and a point above the interface. I want to close all of this slowly by reminding you we want to get how much heat is being released by this reaction rate. Okay. Well, so we can relate that to the reaction rate, I should have said, right? Okay, so we take those 2 points and we start looking at the temperature. And the first question is, again, can we even detect a different temperature when it forms from when it doesn't form? So any difference between the red and the blue, right, means that if the red is higher, some heat was released into the flow. There's no other way for this to occur. Again, this is not a single run, okay? It's an ensemble average. And the answer is yes. In most cases, we can detect changes. In some cases, the changes are significant, okay? Both inside and outside, actually more inside than outside because this is more confined, and outside, yes, there's a much bigger domain, so it's easy for this temperature gradient to be lost through diffusion. Okay, I'm going to show you 2 slides and then I'll close. We have the temperature. Temperature for an experimentalist is kind of 80% of the problem because from the temperature now you can start deriving the quantities that you want, right? So here, you can take, I mentioned before, the gradients of the temperature. Easier said than done, by the way, because close to an interface is difficult to get a temperature because you can never measure at the interface. You can only measure close to an interface. But anyway, let's not make this more difficult than it has to be. So we can take these derivatives. You can try to measure fluxes with them without the hydrates for different conditions. Ongoing work, I don't want to bore you. And I'm going to close by then saying 2 even more complex and I guess from an engineering perspective, useful quantities. Flux is not a useful quantity. A heat transfer coefficient is a useful quantity for an engineer because I can design something. Right? And then you can define your heat transfer coefficient, and you can see whether, for example, when the hydrate forms or not, whether there's some kind of change in the hydrodynamics or other conditions of the problem. But we're 1 step before what I promised you we're trying to do. We haven't finished it. This is still ongoing work. The next step is for us to kind of take some of this and go to the final step. But you can see we're already trying to get there, right? We're already getting the gradients. And the gradients, we can go to where we want to go. Okay, so I don't know how I'm doing with time. Is it okay? So I just want to take like a couple of minutes to summarize really what I told you about today. When you have interfacial flows, multi-phase flows, right, with two different phases, two different fluid phases, or even solid phase I showed you, right? And you try to do optical measurements. And why do you want to do optical measurements? Because you can get some very nice information about the physics, okay? But when you try to apply those methods, most people know, I mean, these are old methods, okay? So these types of problems, you have difficulties. They're not easy. So I showed you, I hope, some problems, right? We have in different types of flows. The more complex the flow, the bigger the problems. And we have to be satisfied with bigger errors. That's how experiments work. Simple flow, easy to measure. You can do that like a complicated flow, right? Okay, you have to give something away. And I showed you, the development of some techniques from beginning where we had no temperatures, right? And there was a flat domain with very little curvature, to adding the curvature, right? To adding the temperature, having a thermal problem, having to measure temperature fields and velocity field. Then we went from there to boiling, then we went from there to phase change, and in the end we even added reaction. So a very, very wide range of problems, always with the view of trying to understand, right? Velocity fields, temperature fields, to understand hydrodynamics, thermal performance, right? And I think if you have some new thing that you learned today, I'll be very happy to answer your questions. I'll pass it back to my host, Professor Mori. Over to you.
Thank you for the excellent talk. So are there any questions from the participants?
So my question is very simple. So you use a two dye, no? What is the effect of the two dyes on surface tension, especially in the case of water, if we use? Maybe for the HFE 7100, it's okay because so much change. But in case of water, so small contamination influences the surface tension.
Correct. So what we tend to do in these cases is two styles of measurements to try to understand. I had a slide, but I think I got rid of it because of time. So we can do two tests. The first type of test is very empirical. So we can say, okay, we have a boiling flow, for example. Okay, in a boiling flow, we can measure quantities with a high-speed camera. Bubble detachment diameter, frequencies, something. Okay, we can pick a number of those parameters. We can measure those parameters with and without the dye. And then we can check whether the physics at a very macro scale level are being influenced or not, right? That's one check you can do. Now you can say, well, you might have changed the properties and not really seen it. You might have changed something that you can't really observe at this macro level. I agree, we don't know. But at least we can check that at the macro level, we're not changing important flow parameters. Sorry, I shouldn't say flow parameter, problem parameter. The second thing you can do is measure surface tension as a function of the concentration of the dye that you're using. So what we did here is we took water, in the ionized water. We did 5 to 10 tests. We have a mean and a standard deviation of the surface tension and a tension mean. We then say, fine, let's add one of those two dyes at different concentrations. Each concentration we measure 10 to 10 times. We have a mean value and an error bar, which is really not really an error, but a variability, I guess, from the instrument or whatever. And we can plot that. And we can keep on doing that for a range of concentrations. Then we add the second dye. So we have the two dyes. Then we add the particles. So now we have the effect of every one of those dyes separately and all of them together plus the particles as a function of concentration. And zero concentration means pure water. And you can see that at some point, so basically what you get is, of course, 0 is 0, and then you start having some effect where the surface tension starts to go up. Now, what you need to ensure is that your measurements are basically below this point, where the concentration of the dye is so dilute that you can say I'm close to basically that dye not being there, purely from a surface tension measurement. This is in the paper. I can share it with you, but it's a very important comment. Everyone wants to know this. Are we affecting the properties? Yes. We're just trying to make that effect small. What does that mean? I don't know. I think there's still some work to do there. I would like to see someone do some study. We didn't have time. Thank you.
Thank you so much. Thank you for the talk. And it's usually heat transfer we want to know that maybe from the wall temperature and the wall heat flux from the solid side. Maybe it's usually maybe people try to understand something, but maybe in your technique and skill, maybe we can understand from the heat transfer from the liquid side. So, but when you some case is a high temperature cooling is a quenching phenomena case. Means temperature drop is very high and very temperature gradient is very strict. It's very big. In that case, it's the interface temperature. Is it okay to know from this kind of technique?
Okay, sorry. I think I got the question, but if I don't answer it correctly, please tell me, all right? So yeah, we've done a lot of work on temperature distributions inside fluid domains, but not exclusively. I mean, I think I showed 2 or 3 different types of flows where the wall temperature is being measured simultaneously. This is one example, right? So these are temperature and heat flux measurements on the wall, right? So we try to do both, and I think both have a role to play for different things. You kind of understand different things. The wall, of course, tells you ultimately, right, what the solid is experiencing, full stop. The fluid tells you why some things might be happening, okay? But anyway, let me go to your question. It's true. In some cases, it depends on your problem. In some cases, the dominant heat transfer process is an interaction between the fluid domain and the wall. And in some cases, the dominant heat transfer problem is an interfacial heat transfer problem. So for example, this is a very good problem. This is a very good case for this, the hydrate formation, okay? So in the literature, what's special about this type of flow that I like? Yeah? So in the literature, the common problem doesn't look like this. The common problem looks like a droplet stuck on a solid. And this is a model for what happens, for example, when you have rain falling on aircraft wings and you don't want them to ice. So a lot of people have done work on this, including a very good friend of mine at ETH. Their work, okay. The dominant heat transfer problem there is basically interaction between air, by the way, right? Between the liquid and the solid. And then you can control it through patterning. You probably know Bully-Gagos-Ataro and so on. Then you can play nice games on the surface and so on. But in this problem here, the wall does play a role, but the dominant, this reaction is happening at the interface. What's happening here is very little effect on it. So it depends on the problem. In some cases, and I think I agree with you, in some cases, you need to focus on the wall and you don't really care too much. It's kind of supplementary information. In other cases, the dominant process is happening here and this is supplementary information. It depends. You can't say one is more important than the other. It depends on the problem.
Any question? Yeah.
Thank you very much for your very interesting talk. So we know that we can get a lot of information by using the fluorescence intensivity. So we can get a lot of parameters. So what do you think about measure 2 or more parameters at the same time? And do you have any commands on what should we take care? Like temperature, pH, or concentration?
Okay. Right. Yeah, the answer is, of course, it can be done. Concentration, is this okay? You can hear me? Yeah? So concentration measurements are relatively straightforward. A lot of people have done measurements with planar laser-induced fluorescence for concentration. Actually, I started my talk by saying I came from the combustion community, and at that time I was dealing with gaseous flows mixing. So you have a sort of a fuel, right? You have an oxidizer, and then the fuel and the oxidizer, two gases, and then a mix. And there, the challenge is not so much the temperature, but it's to kind of measure this mixing field, right? Down to very, very small scales. And then that's actually where I started. So it's possible to do these types of measurements, and they're done quite frequently. Now, if you have a temperature and a concentration that you want to measure simultaneously, again, it's possible. But then you start having to have a method with two dyes or with two lasers or something. Again, so you're making the problem such that you have two unknowns, right? And when you have two unknowns and one equation, which is one image, that's it, right? Game over. You need at least two images to resolve, to solve for those two unknowns that you have. It's possible. You could, as I said before, you can add two dyes and one laser. You can have two lasers and one dye because the dye's emission is a function of the excitation energy, wavelength, I should say. So yes, it's possible to do these measurements, and they have been done. People have measured concentration and temperature. Sure.
Any question?
Maybe I'll ask a question too, just out of curiosity. First of all, thank you very much for the very nice talk. And you show a lot of different problems that you solved mainly with laser-based techniques. And you have said that essentially when we have a two-phase flow, we have a lot of reflections because we have a lot of interfaces that are changing. So I have a question. Have you ever tried non-laser techniques to infer the liquid temperatures? Do you foresee any, or should we go with the laser, or do we have possibility to skip the laser and maybe try futuristic creative ways to get the temperature of a liquid?
Do you have anything in mind? Yes, there are other ways. I actually thought in the beginning that you were referring to more intrusive old school type methods, which by the way, have their own use. Yes, of course, there are so many different techniques and I didn't go into it. I mean, so these days, you could even go, so one of the funny things is people use the word laser, okay, and they think of visible, right? But in principle, it's an electromagnetic wave and an X-ray is just another wavelength of light, right? So yeah, so there are people that have used X-rays. I did some X-rays some time ago. There are people that use gamma ray sources. We had some gamma ray sources, we got rid of them. And these, so X-rays and gamma ray sources don't have the type of problems that we have. They have other problems. We don't have time to go into it. I would just say there's an advantage and a disadvantage of both. And depending on your problem, it'll be the right approach, okay? By the way, one of the complexities is not just experimental. For anyone that knows, if you want to buy a high-speed, high-resolution X-ray system, right? You basically have to sell this building and maybe the building next door, all right? So there's a cost element to this as well, right? It's very expensive to do these measurements, right? Professor Mori, you know, we were talking before about the laser, okay. So I would say, yes, there are different techniques. Okay, I have focused on this. It doesn't mean it's the right thing, but we're pushing the boundaries on each one. So there are people working on X-rays, they're pushing the boundaries in some directions, us doing this, other people doing other things. And in the end, I think it's just good to progress on all fronts because it gives people options, right? To study different problems. Who knows what's best? It depends on your problem. Okay, thank you. Good question.
Can I have one question? So as you mentioned, it's not easy to measure that shape of the interface is complicated. So do you have some good idea to do that? Because once the surface is complicated, because of the reflection problem. So I'd like to ask you, do you have some idea to solve that problem?
I have a lot of ideas, but none of them are good.
secret. Okay.
No. I didn't mean it secret. I didn't mean it secret. So I will tell you my answer to this. When I first started looking at this problem, inspired by the late and great Professor Hewitt, that some of us know, I first looked at something called the downwards annular flow. When you start, so it's a film inside a pipe that's going downwards, and it can go just by gravity, in which case the films are relatively low dimensional. Fancy word for saying smooth, okay? And if you have a gas in the core of the pipe, they can get very, very agitated. The interface can be very agitated. And at that time, when I started looking at this problem with Professor Hewitt, we did a range of experiments over different, let's say, parameter ranges. And you can find that in some cases, when the gas velocity is very high, right, and the shear is very high, you can't even you can't even look at an image by eye and say where the interface is. I mean, you cannot discriminate an interface. There's so much gas that goes into the liquid, gets entrained into so much liquid that goes into the gas with droplets everywhere. It's a very complicated situation. There are some ways to approach this, but they're not perfect. In that super complex interface case, I don't have the answers, but I think it's an interesting area, and I know that you're working on this, and I'm actually excited in maybe coming up with some solutions to this problem, because I really do think that when the interface gets very complex, it's an unknown quantity. I can't give you an answer. I don't know. All right.
Any other question? Okay. Oh, it's last question.
Easy only, please.
Thank you very much for your nice talk and introducing us a lot of optical techniques. I'm interested in the temperature measurement by fluorescence. So I think, I'm not sure it's rhodomy B or something. So you showed us a figure that the sensitivity of rhodomy B on temperature. I want to know the calibration system, including the camera. So I think you need to
remember which flow problem I showed that for? Because these are different systems for different experiments over 20 years. So I don't know which one.
All right. So the temperature measurement, I think you showed us it two peaks.
Those are not cameras.
Yeah, I think, yeah, it's a sensitivity of rhodomy B on temperature.
Sorry. Yes, and I know what you mean. That's not a camera. Yes, it's a good question. This is in a spectrophotometer.
Yes.
A camera.
Yes.
So the laser and a camera.
Yeah, I understand that. So
if you need the specs, I don't know what they are. I can send them to you later. Which device we're using exactly.
Yes. So after that, I think you need to calibrate the camera to convert the brightness to temperature.
Correct.
I want to know the way.
I will send it to you. I mean, I should say, right, these are not published results yet. I mean, did I put something in here? Yeah, so there's the camera there, but if you want specs, I can send them to you later. Let me see, did I put them in here? If I didn't put them in here, then I need to find them and send them to you. Okay. But yes, there has to be a separate calibration process in situ, right? I'm reading the paper that they wrote right now, correcting it.
Thank you very much.
Okay.
So thank you for the nice discussion, and thank you for the very interesting and impressive talk. And I'd like to close this session. So please give the big round of applause to Christos.